Estamos no ar?
Sim.
Ótimo. Então, olá a todos. Um bom dia. É com muito prazer que nós começamos mais um webinário internacional da Unifesp. E hoje nós temos um ilustre convidado que está literalmente 12 horas de diferença praticamente nossa. Então, respeito ao nosso convidado, o idioma deste webinário será em francês. Opa, perdão, em inglês. Sorry. So, welcome, everyone. Thank you so much for being here with us today. It's a great pleasure to introduce our guest today and also our host today, because Professor Kenchan, she worked hard to organize this webinar for this morning, and she brought a very, very special guest today, which is Professor Xiaohui Liu. And Professor Xiaohui Liu, he's from the University of Chinese Academy of Science, from the School of Physical Science. So today he's going to talk a little bit about the nuclear hadron physics, the charming physics in the BESIII project. But now my role here today is to say thank you, Professor Xiaohui, for being with us today. On behalf of the Graduate Studies and Research Office of Unifesp, it's a huge pleasure to receive a Chinese research here with a very well-concepted and well-known field of research, which is quite important for Unifesp because we're pretty new on physics. And just as the health area, we also want to improve our physics area. So it's pretty important, and mostly important is to have Professor Kenchan with us, which is a woman. And also, it's not a Brazilian by the birth, but it's very welcome by Unifesp as one of our faculty. It's pretty important to have a woman that is in the science, especially in a hard science like physics, to work and to prove to the world that yes, woman power is here, and we have her to work with us at Unifesp. Professor Kenchan, you have no idea how pleasure is to have you between us and representing us in such an important field of knowledge, which is physics. Professor Kenchan, she's from India, and she's an assistant professor of the Department of Physics at Unifesp in Campus Diadema. And she had a previous position at the University of Rio de Janeiro, and she has different academic experiences, and which she had a doctorate from the University of Mumbai, a postdoc at the University of Valencia in Spain, and University of Coimbra, Portugal, and at a research center for nuclear physics, Japan, and at the University of São Paulo here in Brazil. Her interests in research are interactions of hadrons and properties of hadrons, and her research collaborators are with the theory groups at the University of Valencia, Research Center for Nuclear Physics in Japan, Binhan University in China, and Pukyong National University, South Korea. So, Professor, thank you so much for organizing this webinar. I'll let this stage for you to introduce Professor Xiaohui and also Professor Marina, which is a very important name in the area. And I hope you all enjoy this webinar. Please welcome everyone, and Unifesp is all arms for you, and it's our time to listen to what you have to teach us. Thank you so much.
Thank you very much, Professor Camilo. That was very kind of you. And every word you said, I really felt very nice, very, very kind of you. And my job is now to just say a few words about Xiaohui, and I just want to listen more from Xiaohui, so I'm not going to take a lot of time. I'm just going to quickly say Xiaohui, as Professor Camilo already mentioned, he is a professor at the School of Physical Science, University of Chinese Academy of Sciences. He has his undergraduate studies done from Peking University, and he has done his doctorate from Tokyo Tech, Tokyo Institute of Technology. He is involved in the BESIII project in the Beijing Electron-Positron Collider, the BEPSI-2 facility in China. He's also involved in the LHCb project. He is doing amazing work. He's in the last 5 years, his average number of publication is like 80. So you are going to. I'm really looking forward to what you're going to teach us, and I'm very thankful to you, Xiaohui. Just before we begin, and I leave. I ask you to begin the talk. I would just like everyone in the audience to please keep the cameras and the microphone not switched off during the talk. We will ask the questions at the end. And when you want to ask the questions, you are welcome to open your microphone and just directly interact with Xiaohui. I think if it's like 2 cameras at the same time, probably we can even handle that. So anybody in the audience who wants to ask the question is also welcome to open the camera and interact with Xiaohui. So that's most I have to say. Xiaohui, welcome, and please begin your talk. Thank you very much.
Okay. Thank you, Kenshin, for the. I think it's my honor to present the BESIII results in this webinar. Thanks the invitation from Kenshin, and also for the very nice introduction by Professor Camilo, and also the very distinguished Professor Melina. And actually, my institute is the University of China Academy of Sciences. Actually, as Professor Kenshin introduced, we are all not only attending the BESIII experiment, but also LCB. And in LCB collaboration, we actually have the Brazilian colleagues from Rio group. And actually, we in our group, we have a colleague named is Daniel Viela, who is graduated from Rio group and working as a postdoc in our group. Then he just moved to Cincinnati University in USA. So actually, Daniel told me a lot about the community in Brazil. So that's why I was very glad to accept the invitation and give this speech, and hope to share knowledge with the Brazilian colleagues, and hope we can get more future collaboration in different aspects of in the hadron physics, and also nuclear physics, and also other part. Okay, so my outline today, I will mainly highlight some results from BESIII after some introduction of this facility. And then I will also give you some information about the future plan in China. So later, at last is the summary. So you know that in the current study of the standard model and also searching for new physics beyond it, so there are different kind of aspects we can work on. For example, there is the high energy frontier. For example, the Hadron, and also the current running RST experiment, and also there is also a high precision frontier, which give very precise measurement about some asymmetry and also flavor, lepton flavor universality, and also any lepton number violation and so on. Many this kind of precision measurement, and also the G-2 measurement. For example, tomorrow there will be a release of a new G-2 result from Fermilab, and also EDM. So it's a very stringent test on the standard model, and could find some clue about the new physics. And also there is a low energy frontier. So we study the hadrons and also the low Q-square strong interaction, if non-perturbative effect, and also some confinement, the south of the confinement and so on. So it's basically about the low energy frontier. So my talk will be basically cover the both sides of the low energy frontier and also the high precision frontier. So our main task is to understand non-perturbative effect in QCD, and a possible input to constrain the standard model and also to search for new physics. So our target or our research object is to study the hadrons, which involve the charm quark, which is around the 1.3 GeV. And this is kind of like we can probe the QCD just below the perturbative QCD, which is kind of like among the non-perturbative and perturbative transition region. Not only for this, but also we could use some decay from the charm hadrons goes to the lighter hadron. For example, the hadron with stringness and also with only UD quark. So it's a very important playground to study the strong interaction. So as you know that there are many from the history that were many different kind of facilities to aiming for study of the charm. It's from the 60s in the last century till now. There were collider in Frascati, in SLAC in USA, and also in China we built the first version of Beijing electron-positron collider in 90s last century, and then we update it to the second version of BEPC2 and start from 2008 until now. And there were also machine in Cornell, which called CSR, is a Chloe experiment, and also there is also a machine in Novospeak, which is also actually that were running until now. So if you see these machines, you see that their luminosity is getting increased with from the old period to now. And now this is BPC2, which from 2008 to now, and still we have planned to continue its running maybe to 2025 or even later. And now also I will give you a little bit of information of the future plan in China. It's called the Super Taochang Factory with luminosity around 100 times higher than the current running one. Okay, so for the BPC2, it's located in Beijing, and also my university is also in Beijing. So we actually, my university is just sharing one big campus with this facility. So it's just like 10 kilometers from Tiananmen Square. So it's very proper sector in Beijing. So if you have time, welcome to visit. So this collider is running the electron-positron beams, and each beam has energy from 1 GeV to 2.3 GeV. And last year, during the COVID-19 period, actually we never stopped work. So we updated the energy to 2.45 GeV, which expand our physics topics a little bit more. So that's why we have new findings. I will introduce later. So there is one white detector at the collision point. It's called the BESIII spectrometer 3 because it's the third generation of this BESIII spectrometer. So we started experiment in 2008, and which is only is in the test mode. And from 2009 until now, we are doing the really physics run. So each year we collect many data, and we reach the design luminosity of 10 to 33 per square meter in 2016. So it's also actually the highest luminosity machine in this energy region. So the bottom chart shows the current performance of this machine. So the dotted line shows the theoretical peaking luminosity at different energy at a different beam energy, and you'll see that we are optimized this machine around the 1.85 GeV, which roughly corresponds to the charmonium state PSI 3770, which is used for the DD bar data taking, and then getting down with the beam increase. And actually, we already take data at a different energy point. This is the schematic layout of the BESIII detector. So it's a very generic, the generic purpose spectrometer. It's symmetric to the beam pipe, and the most inner side is the main drift chamber, which has small cell and with the helium gas, and also with very good space resolution and also momentum resolution, and also we use DDX method to do the particle identification for the charge tracks, and a little bit outside is the time of flight detector, which also has a very good time resolution around 80 picosecond in the barrel part, and also a little bit worse at the end cap part is around 110 picosecond. However, in 2015, we upgrade this part with the MRPC, the multivariate resistor plate, to replace the previous scintillator, plastic scintillator, and then reach much better resolution to 60 picosecond. And surrounding the time of flight is the electromagnetic calorimeter, which is using CSI crystals and with a very good energy resolution for the photon energy measurement, and also used for the electron identification. Then a little bit outside is the solenoid magnet, which is supporting the one Tesla within this inside the drift chamber for the momentum resolution, for the momentum measurement. And also we have the muon counter with the 6-layer RPC, and to do the muon identification. And so this detector actually is very good for this kind of low energy collider. Actually work very well, and for the last 12 years. So it's very robust. And this is a little bit more details about the specifics of different parts. So I might just skip it. okay, we have very good particle ID capacity. So you see that from the DDX measurements for the proton, cation, pion, and so on, we have good separation until 1 GeV, and also it incorporates with the time of flight counter. So it's we can perform very well K-pi separation for momentum lower than 1 GeV. And this is the current BESIII collaboration. So there are around 15 countries and 72 institutes and around 500 members from China, from Europe, and from USA, and also from other Asian countries like India, Pakistan, and Turkey, and Thailand, and so on. So I think it's a very active collaboration, and we have very good outcome. For example, until now, we actually have published 300 papers. So from 2010 and now each year we publish around 40 papers, and 1/5 of them is PIL papers. So from the 2008, 2009 to 2021, so we collect many data points from 2 GeV up to 4.95 GeV. So, and also we take very high static data at germanium state peak. For example, BESIII, we take like 10 billion GSI events until by 2019. This is the largest BESIII example in the world. And also now we are taking very high statics Psi2S example. Our target is 4 billion. And also very statics of the DD bar example at Psi 3770. And also some energy scan about 3.8 GeV until 4.95. So here we can study some exotic germanium-like states and so on. And also some lambda-C example for germ-bion study. So this is the current, basically explain the physics we can study at BESIII. So from 2 GeV to 3 GeV, so this region is kind of like a very smooth. From the R value, you could see that it's a very smooth distribution. So here it's correspond to the low Q-square energy region. So we could study some Hadron pair threshold effect. For example, the baryon pair, the lambda pair, the sigma pair, and also the cascade pair. So we could study their production. And also their operation and also their decay through some quantum correlation in the production process, and also some light hadron rarities like Y2175, and also study the R to measure price measurement of R value, and also some multi-pion production cross-section, which is important as input to the J-2 calculation, and also the fragmentation function, and so on. And also above the little bit above energy from 3.1 GeV to 3.7 GeV, we take data at germanium peak like BESIII and Psi2S. So through its decays, we could study the some light hadron spectroscopy, and also some global search, and also using the very high statics germanium peak data, we could look for some rare process like lepton flavor violation or CP violation of the hyperon decays, and also some rare and forbidden decays. And also one important result from BESS is the tau mass measurement, which is very important for the electroweak theory. And also above the DD bar threshold, we until the uppermost energy, we could study the so-called XYZ energy region for XYZ study, and also study the D meson decays and also DD0 mixing, and also some their strong phase measurement, and also charm biome decays, and so on. So it's a very rich program. So I would a little bit elaborate some highlights of the current BESIII achievement. For example, why it's called the charm factory? It's because it produces very high statics charm biome or charm meson, and also it has a very unique physics advantage. For example, in the near threshold, if the two D0 and D0 bar they are produced in a quantum coherent state of C out quantum coherence, so we could access the D decays by using this quantum coherent information. We could access some unique information. For example, the D0 decay strong phase and so on. And also the 2D is produced, the 2D0 bar here is produced at rest. So when one D0 is measured or detected, then we could postulate that the other side must exist another opposite charm D method. So it's so-called tag and also the double tag method. Similar logic also applies for the lambda C pair production. So because it's also produced at a threshold, the threshold of the two lambda C pair. So the two lambda C also has some correlation in spin correlation, and also there we could also use the so-called tag method. So there is one very clean observable for the D decay is to measure its D goes to purely lepton final state. So leptonic final states mean that it will decay to either charged lepton or the neutrino. So through this process, we could well separate the electroweak part and also the hadronic part. So we could use this decay to extract the most precise direct measurement of the VCD or VCS, and also by introducing the lattice calculation of the decay constant, which calculates the hadronic part very precisely. And also there is another important reaction is D semi-leptonic decays, which D goes to one hadron or two hadrons and so on plus two leptons. So this process actually that we can access the so-called the Q-square dependent form factors from the D to meson P, and this form factor information will reflect the involved non-perturbative effect, which can calibrate the QCD models and also lattice QCD. And also a little bit more complex part is the D hadronic decays, which could test the isospin effect in charm decays and also SU3 flavor symmetry, and also many different decay mechanics with respect to the different amplitude, tree diagram, and also penguin and so on. So there also involves many difficult issues in non-perturbative QCD, for example, the long distance effect, final state interaction, and so on. So all this information from experiments will definitely improve our understanding of the QCD model. So one of the main physics is to determine the CKM metric elements VCS, VCD. So we expect that at BESIII we could provide the direct measurement of these two elements with precision much better than 2%. And also we could use the BESIII measurements of the strong phase to combine with the B factory measurement of the B decays to D-mersum plus Hadron to measure the CKM unitarity triangle gamma angle. So it's very important to over-constrain the CKM matrix, and then to try to find a hint of the new physics or the new source of circulation. So the idea is that with this the pair production at near threshold, so neither D-mersum or lambda C baryon, so we could use the many kinematic constraints and also the missing mass technique to reconstruct the neutrino in the final state. So this is a very unique at BESIII, which is a little bit difficult for other experiments. So, for example, I will first a little bit introduce the Chapman-Mason decays. So, we measured the many different Chapman-Mason purely leptonic decays. For example, D plus to mu, and you see very clean signal around 0 for this missing mass square, which corresponds to the neutrino mass. So you see that a very clean signal and a very well-modeled background, and with very good precision of around 5%. And also we measured published the ds goes to mu nu, and the ds goes to tau nu, which tau goes to pi nu. So so you will see that this dotted blue line represents the ds to tau nu signals. So this is the most prized measurement in the world about this purely leptonic decay at branching ratio. So through this branching ratio, we could extract the VCD and the VCS in the most precise way. So you will see that from this purely leptonic decay, you will see that from BESIII, we can borrow the calculation from lattice QCD, which is show the yellow band. It's from the lattice QCD, and if you can compare with the BESIII measurement of this FD plus, you see that this is really quite advanced in precision. Similar case for the DS decay constant, we see that the above all lattice group, and you see very precise measurement. So we could actually borrow their calculation and then input to this equation, and then extract. So this part will be input, and then we can extract this VCD and VCS. Okay, so also I would mention about this D or DS semi-leptonic decays. So this part we can measure this form factor by with the input of the VCD or VCS, and also we can also use the calculated form factor to extract the VCD or VCS. So it's a different depends on how you would use this result. So we measured the most precise measurement of the D to K minus E nu and D to pi minus E nu, and also the D plus and to K or D plus to pi 0, and also this is the DS to eta and the DS to eta prime. So you see very clean signals and a well-controlled background. So these are all very most precise results. And also causing mu channel, we could do similar way. So this is the D0 to pi nu and the D plus to pi nu. and also the D0 to K mu, and also D plus to K0, D plus to K mu nu. So these are all the most precise one. And from this measurement, we could input the VCD or VCS and extract the form factor. So you see that the BESIII provides the most precise form factor measurement for the D to K or the D to pi form factor. You'll see that this yellow band again represents the lattice QCD calculation. So you'll see that the BESIII measurement would really precisely calibrate the lattice QCD calculation. So we see that the future BESIII will accumulate 5 times more D data. So the future precision would be much better than the current result for the D to K or D to pi channels. So we would expect that the lattice QCD will need more efforts to reduce their uncertainty and then compare with BESIII measurement. And also, this is the DS to eta and eta prime form factor measurement. So you see that the BESIII results actually have strong evidence of the deviation from the lattice QCD calculation for the DS to eta. So it means that the lattice group need some periods on this work maybe need some modification in their calculation, and also for these two calculations. So for the DS to eta prime, because the error bar from BESS is a little bit large. All these measurements are the first one in the world. So there's only experiment information now for these two form factors. Okay, here I show the best precision of the VCD and the VCS measurement from BESS. It's all based on the purely leptonic decays. You see, these are the BESIII current best measurement of BESIII, VCD and also VCS. And you will see that the BESIII measurement is the best, and so the future would be that we want to improve this precision in order to compare with the worldwide fit result, because this yellow band shows the PDG value, which is obtained from the indirect measurement by considering the CKM matrix elements, CKM matrix. So means that the current value seems have some deviation from the direct measurement. So we would in the future try to do better and to solve whether there is a real deviation from the current result. So this is the prospects for with the 5 more data sets, and so we will see in the future. And also we could study the lepton flavor universality. This is some it's like the to compare the D goes to mu semi-lepton mode, and also the D goes to electron semi mode. So the ratio can cancel out many QCD hadronic uncertainty, and expect that this ratio could be more sensitive to the contribution from the new physics. I think the most sensitive part is the RDS, which measures the DS go to tau nu over DS to mu nu. So we expect that this could provide some hint or constraint to the some new physics model. And again, BESIII published the strong phase measurement of the D to K short HH. So this is a kind of self-conjugate three-body process, which can be combined with the B factory measurement of the B goes to DH, and we could extract the gamma angle with the so-called BPGGSA method. And also, it's useful to extract the charm mixing parameters by using this charm strong phase information. And BESIII again taking advantage its quantum coherence production, so it could directly measure its strong phase. So we published the D2 K-short pi and D2 K-short KK, and with this input, the recent RCB gamma angle and measurement have published their results, showing that our results as input to the gamma measurement at RCB would reduce the relevant systematics down to 1 degree. So it's very important because in the future the run 3 of the RCB they will reduce the total uncertainty of the gamma better than 1 degree. So it's this input is very important for the future RCB measurement about gamma angle. Also, I would mention a little bit the current lambda C charm baryon decays at the BESIII. So you see, we published many results from 2015 until now. And this lambda C is interesting because it's the lightest charm baryon, and with UD is with naive quark model that UD is in the no spin and no iso spin 0 and spin 0 UD diquark and another heavier charm quark. So this kind of like a very naive picture. So in some sense, this its decay can be compared with the D meson or DS meson in order to understand the non-perturbative effect QSD inside the charm decays. So we published a few interesting results. For example, we published the first absolute measurement of lambda C hadronic decays using the threshold data. We use the so-called double tag over single tag measurement to measure this the relative decay rate, which can give kind of like a model independent branching ratio measurement. So we provide we combine the 12 hadronic mode and do a simultaneous global fit. So we obtain a very precise results of the branching ratio of the 12 hadronic modes, which are all the most precise one compared to the PTG results, and this results actually help the many different charm baryon models to calibrate their parameters. And also we do the first measurement of the absolute branching ratio for the lambda C to lambda E nu. So this is the largest branching decay mode, branching mode for the lambda C decays with the leptons in the final state, and we use the so-called missing mass energy method to see a very clean signal around 0, which corresponds to the neutrino, because there is one missing particle in the final state, and we provide the most precise measurement of the branching ratio of this semi-leptonic decay. And also this triggers the first lattice calculation of the lambda C semi-leptonic decays. So their calculation shows that the branching ratio results is consistent with BESIII results, and also they provide the Q-square dependent form factor or Q-square dependent partial waves of this decay mode. So in the future, we will have 10 more lambda data on tape now. So we will gonna measure the form factor and then compare with the lattice calculation. So then I move to the Hadron landscape. So you see that BESIII not only studies the Chang-Bion or Chang-Mason decays, actually they can study many different kinds of hadron, especially the hadron spectroscopy. There are two ways to do that. One is that it's through the germanium radial decays to study the light hadrons, which the light hadron means that it consists only light quarks for the UDS quark. We are now already have 10 billion GSI on tape and also 0.4 billion Psi2S. So you that this light hadron actually have energy, have mass around below 2.5 GeV, and so we could study their properties with the partial wave analysis. And also we can study the heavy hadrons, which consist of the charm quark. So so we basically, for this kind of heavy hadrons, for example, with the for this CC bar, QQ bar, its mass is around 3 GeV to 5 GeV. So we at BESIII we could directly produce it through the direct production or the radiative or hadronic transition. So we use data about 3.0 GeV. So the right panel shows the data we have collected used for XYZ studies. So about 3.8 GeV, around 23 inverse Findbar. So it takes around 6 or 7 years so far. One important physics we want to entangle is that there are overpopulated germanium spectrum. You will see that there are many predicted normal germanium states, which show the rectangle here. However, there are also many confirmed. For example, for the state below the open charm threshold or the DD bar mass threshold, it's while the experimental observation is well consistent with the theoretical prediction. However, above the DD bar, you see that we see many structures or states in experiment. However, they are actually not real consistent or agree with the theoretical predictions. So there are some of them are neutral states, some of them are charged states. So we call this state is XYZ state, means that they are not we are not sure about their exact property, and so that's, however, one interesting feature that all these states, so-called XYZ states, they are very close to some the pair of terms. So there are theoretical models explain that some of this state actually is not a real particle, but some couple channel effect or some cusp effect and so on. So so it means that it's really a little bit complex for the moment, but it deserves more efforts to really understand their nature. So the first set of XYZ studies from BESIII is we discovered 4 charged states in 2013 and 2014. So we have very famous ZC13900 observed in E plus E minus go to pi plus pi minus GSI in the environmental spectrum of charged pion plus a GSI. So it's a very narrow peak around 3.9 GeV. And we cannot explain it with any of the pi resonances, so we attribute it to as a new state of the pi GSI. And also we observe the similar enhancement with very close mass in the e plus minus 2 pi dd star. And near this dd star threshold, we see very sharp peak with very narrow ways enhancement, and its mass is very close to ZC3900, and they are charged. So they are regarded as the so-called tetraquark candidate. And also in the E plus E minus go to pi plus pi minus Hc. In the environmental charged pion and Hc final state, we also a sharp peak around 4.02 GeV. And so also cannot explained by any pi randomness. A similar thing happens to the E plus E minus 2 charged pion plus 2d star, which are a charged pair. So you see that for this over the sum of the charge is charged of the d star bar. So you see the enhancement around the threshold of d star. So and also their mass are very close. So that's happened by 2014. And later we measure this ZC3900 using the very more data set at 4.23 and 4.6 GeV, and we do the partial wave analysis, and we measure its spin parity is favor 1 plus. It's also consistent with many theoretical predictions. And also we find later 2 years we also find their corresponding iso spin partners, because as they are charged, so they should have iso spin 1, so they should exist the neutral partner. So we found 4 partners for each of them. For example, we have neutral ZC3900 and ZC4020 and ZC3995 and also ZC2025. So they all find the corresponding neutral part, and so this all the ZC states are very well established. Especially ZC3900 is also being confirmed at Clio C results. So the question that since this ZC state contains UD quark and CC bar, if they are real code, so they should it's the corresponding SU3 counterpart, so-called ZC state with stress. So it's like replace the D quark with the F quark. So it's ZC. There are the main ways and the information for conversion. So for now, we always attribute ZC3900, ZC885 similar. They are one state, but didn't decay mode. And also attribute 4020 and 4020. They are one state, but 2 different decay mode. However, this is just an easy sum. So further work needs to really understand whether they are same state or they are actually different. So actually more ongoing S3 with some couple channel amplitude analysis and so on. Okay, talking about the test, so it also goes to the new taking in last year. So last year upgrade our energy beyond 4 to 3 GeV, means that the total of the energy goes beyond the 4.6 GeV. So we take 5 energy points from 4.2 62 to 7 plus 1 luminary energy point. So in the last year, we analyzed this data. Target is to actually today is the Y, so the Y of 630 and Y 4660 because they are this 60 actually by observed by Babar. It's another state. You will see in the experimenter. Also, Y660 is observed by Bio for the C cross section. So we data in this energy points, but we find things. In this set, we use this process so-called plus minus 2D star minus 0 or D class K plus S minus D0 star. So these two processes, the purpose is to look for the so-called ZCS, because I explained in the previous that if they exist, there should be CS if this work well in quark model. So we select to enhance the detection efficiency. We only partial recognition. We detect only K plus and a S minus, and then we call this K and S to look for the star 0. Or we could also recoil the recoil. We also could see this D0 plus pi 0 photon, which peak around this star 0. So see that these are the clean DS signal, and also the requirement of KDS, very clean D star 0 peak. By seeing this candidate out, we plot the requirement can, which come to the DS D star 0 or S star minus 0 in very mass. So we see after we remove background, we see enhancement around below 4G, which corresponds to the marriage code of this D star 0. And you start this plot on the right side. You see very clean gathering around this recurrent mass term. You don't see the kind of structure in the so-called round sample, which represents the curve background. So if you do it to this spectrum, we actually the first hydrogen tetraquark candidate stringless, so-called ZCS 985, and we mass and we measurement which is close to the threshold DS star 0, DS star D. This is interesting. And also, we do simultaneous to different energy, and we see cross section distribution, very clear enhancement around 4.8 G. So that there is some dependence which enhance the ACS protection. If we compare this ZCS with Z, you see that they are almost to the charm medicine pair mass threshold, similar to the ZC or ZB, which corresponds to the DD star, BB star. So it's very interesting, and there are many different models to explain it. Interesting is that before we publish this result, there was one workshop about the charm project in China and also in Russia. So Malik gave a comment on the super charm. One of the important mission of the charm is to find the ZCS. However, we did that before the super charm may be realized. So there are many different scenarios to explain this state. One interesting is for DS785. In case you're gonna exist in molecular model, it's gonna exist only different force. So it's not gonna be a pion exchange pi bond, but some others. For example, neutral one for eta or some others. And also, as you know that after S3 published this is RCB also published their observation with DS 1000, so which in the K GFSI-5, and in the K GFSI spectrum, they report a very broad DS rarity with the partial variances. So, however, the mass is very close, as you see the numbers. However, their weights are very different. The ACC force is around 2 MeV. However, for BESIII, it's only less than 10 MeV. So it's we still are sure what made this difference. Anyway, it's very interesting. Also, report about the Y state. It's called Y because it's a neutral particle which comes directly from E plus annihilation. And from history, the first Y is observed by Barbar. They observed Y260 in the E plus to pi GSI. And later, they report the Y360 pi psi 2, and also Y460 with the combined set of the pi 2s.
Shall we? I'm sorry. Yeah. Your voice is breaking right now, so I don't know if we could just try. You could just switch off and switch on your microphone, because now your voice was breaking in the last few slides a lot. Could we just try that?
So you want what do we do?
So if you could just unplug, just switch off and just click on your microphone and click on it again. Yes, just to try, because your voice was breaking a lot. So, okay, let's try now.
Okay. I said okay.
Okay, please go on. Let's see now.
Okay. Let me continue.
Yes, please.
Okay. So okay, as you said, Barbari published the Y4260 in pi final, and they see line shape the line shape as energy, and at best we did find at a different point we take data and to look for pi GSI finite. We see that at different points there are some variation of this section, especially around the 4.26 GeV. This is a very consistent with observation. If we do the finding, we found that actually the line shape is not simple beginner. There is a structure around 4.2 GeV. So we feed to this fine structure and not only to this high and low luminosity data, but also to the more statics data. So we see that actually there can be size 2. We can explain it the 2 states. One is with mass lower than 4.6 GeV, but 4.22 GeV, the very narrow 40 GeV, and it's a little bit higher mass from the 32 GeV, a little bit wider ways. So that this Y260 actually not one breakwinner, but actually it's considered as a two breakwinner. And this 4.22 G actually been confirmed with different final rates. For example, E plus U2, E plus pi minus C, and omega K0, and eta GSR, and also pi 0 D star minus. So you see that all have be fitted with a regular resonances, which has a mass below 4 to 6 GeV. Also, another higher mass resonances on the 4 to 3 GeV. So it's the new feature of what we see as 3 about this state. And also, I mentioned a bit about the light hadron study at the BESIII. So light hadron usually based on the harmonic radiation. In the below diagram show what different light hadrons the harmonic radiation decays, which is to be a rich, so we look for gluon. Also the gluon with another pair of quark, which is the hybrid, and also other kind of things, maybe 2 quark meson or 4 quark meson, so on. One of the numerous results is so-called XPB bar or XT35 from relative decays. At the BESIII, the second generation S detector, which is the XPB bar constant. This is GEPSI to gamma bar. So this final, if you look at the PB bar MS, it's very clean constant around this threshold. So at the back, we confirm this yield, and only for but also the partial wave analysis and this XPR enhancement with the quantum 0 minus, and its Y is below 36 eV. And so we, in the process of BESIII go photon plus eta prime pi, we see structure around the 0.835 eV around here at the best. This 1835 is also at BESIII with much larger set. So only we call this, but also see more structure. We call XT2022 and X23C. So this X1835 is believed to be connected with the XPR because they are very close. So you said this map is 1836 MeV, and coherent just accent the X1835 is also with SO 1836 MeV. So very interesting. Their mass are different, so we might not sure about the real physics, but we need to look on more things. So actually did the similar different relative decay for GEPSI photon K-short eta, and go to photon omega and photon plus pions and omega eta pi. So all different states action channels, we see bump structure all around the PP bar threshold and all below it, or roughly close.
Sorry, Shahui, we're still
yeah.
your voice is still breaking, so I'm going to ask you to let's try one more thing. How about you switch off your camera? Maybe we hear you better. We want to just try. So just switch off your camera and then please.
Okay, I will. Okay.
Thank you.
Okay. Yeah. Okay. I will continue. Okay. So you see that there are many different final stage which all shown resonance around the PP bar threshold. So with the around 1 billion BESIII event, which completed by 2012, we set in to photon plus prime pi. We very clear bump structure around the 1835, and also later bump. I usually think that if you look carefully at this line around this 18.5, this dotted line shows the mass of 240 proton. So that is the threshold of PP. But you see that on this line, you see very sharp this X in 35 shape. The environment prime pi observed in 2 prime decay channels. One is the photon plus pi, another is the eta plus pi. It's interesting. Means this very significant distortion of the pi line in the XPP bar threshold. So it's very very clear signal that this X bar and X1835 will be very connected and do a feed to this notation and show that TB this feature can be explained by IB bar plus one additional Brewigner resonances around 1820 MeV, 1920 MeV. Or it can be explained by a coherent sum of X1835 plus a narrow Brewigner at 1870. So for the moment, the result is only one divisional fit. So now we are doing more sophisticated partial wave analysis to do the couple channel analysis of this photon plus eta prime pi and photon plus PP bar. So it's ongoing and it will be very interesting. And also for this light hadron spectrum, we have another Y, so-called Y state, is called Phi 2170, which is seen by Barbar and Bell in the direct production of E plus and minus goes to, for example, goes to the Phi 0 Phi, and so BESIII confirms this in the Phi F0 final state. And there are, so at BESIII we do many measurements at a different final state, and we confirm this peak structure around 2.17 GeV. It is explained as many different kind of scenario. The SS bar, the SS grown hybrid, and also some stringent excited states, and also even tetraquark state or molecule state or 2 hyperon, lambda bar, and so on. So it's not clear yet, but anyway, we at BESIII, we look for many different kind of hadron final state, including the lambda, the KK pi pi, and also the 4 kaon and the 5 KK and 5 eta prime and so on. We see structure around this mass region, and so they are. If we compile them all here, so we see that they are similar, quite close or quite similar, and seems that many work need to done to really understand them. Last part I explain is a little bit about the so-called form factor of barons. So in the E-mass collision, we could produce hadrons from at the threshold. For barons, as their mass, their threshold is start from around 2 GeV up to 3 or higher. So BESIII actually is a very nice place to study the threshold effect of the 2 baryon production, and is always connected with the so-called the time-like form factor. That this hadron production can be described by this electromagnetic form factor, and which could reflect its internal structure of the baryons. And this can be complementary to the so-called space-like region, which baryon can be interacted with the virtual photon, and this way the so-called deep elastic scattering and so on, they could in the space in another way to look into its structure. So these two kinds of way can be combined and together to help understand the internal structure of different kinds of hadron. So one interesting thing is that at BESIII, we see very clear enhancement near the threshold of the baryon pair production. For example, if you look at the proton-antiproton cross-section from threshold up to much higher energy, you see the cross-section actually is higher, is the highest near threshold, which goes down as energy goes up. Also, we could measure the form factor through this formula, which this GM is the magnetic part, and also G is the electronic part. And their ratio could be tracked from the angle distribution, and we see we can measure its ratio energy as a function of energy, and also their absolute form factor as a function of energy. And one interesting effect is that if we measure the so-called effective form factor, which is defined as a combination of G and GM, and if we fit with dipole model, we see that there is a deviation from this dipole model with a kind of like fluctuation or so-called oscillation, which is really interesting. So the oscillation is a little bit going down as energy goes up. So this is actually being observed firstly at Barbara experiment in USA, and also we confirmed this oscillation in the data. Also, similar thing happens for neutron, anti-neutron. This measurement is very challenging because neutron and anti-neutron are difficult to detect in the normal spectrometer. So we use 3 different methods to do the measurement. Basically relying on the very fine-tuned time of flight detector and also the electromagnetic parameter. So we realize the experiment, the measurements, and measure the cross-section of the neutron, anti-neutron, and we see a similar enhancement near the threshold This is the cross-section result, and this is the points are best 3 results. And also, these are the ratio of the 2 factor, and these are the absolute form factor of the GMG. If we compare the cross-section between proton, antiproton, and neutron, anti-neutron, you see that the cross-section of the neutron actually is lower than the proton, and the ratio actually is not consistent as energy at different energy point. So there are some variations, especially some drop around 2.2 GeV. But yeah, the theoretical prediction on this is not really being confirmed. So we need, I think the model needs to be improved. Another interesting is that we do also see the oscillation of this effective of form factor relative to dipole model. You see this neutron points, they also oscillate and as energy goes up. This oscillation seems has some phase shift from the neutron oscillation, which is here is shown here as these pink points. So it's very interesting. And also, we could measure this Hadron part, not only nucleon, but also Hadron. So we could produce Hadron at different points, especially near threshold. So the Hadron pair produced, which they are, we could measure the Hadron decays because the Hadron always decay in weak decay. So we could actually probe its polarization. This means that as the 2 Hadron are spin correlated, so their polarization also being correlated. We would do the measurement of the 2 Hadron pair decays and measure this the Hadron polarization as different energy points. So the polarization are formulated, the measurements are formulated in this formula. So this delta phi reflects the polarization of the Hadron at different energy points and also the angle dependence. So you would see that we actually can see the lambda bar pair production as the cross section at energy point goes up, its cross section goes down. It also shows some near threshold enhancement. And we see also kind of like a polarization effect, which is reflected by this delta phi. So another interesting feature that by looking at the lambda bar polarization, we could not only probe this polarization effect, but also this polarization actually can help us to precisely determine the lambda decay asymmetry, because the lambda decay to proton pion is a weak process, and so their influence of the S and P wave could be much well determined by using this 2 spin correlated lambda pair. So we actually consider this lambda to p pi or anti-lambda to anti-proton pi plus. There are 2 decay asymmetry can be measured in a very precise way. So you see this is the new best result, and you see that especially for the lambda to p proton pi minus, the result is much different from the previous experimental results. And actually, this actually correct a long history and an estimation of this decay asymmetry. Why it's gonna affect many measurements which with the lambda involved. in the polarization measurement and the spin measurement. And also BESIII provided the most precise measurement of the anti-lambda decay asymmetry. And this comes to research. And similar can be done for the and so that very so this is seeing positive. This seems delta phi is zero. The negative delta phi value polarization effect. However, in side quest decay sigma, the opposite sign of the polarization. So it's a very interesting feature. So we measure the decaymetry of the sigma with the precision, very nice precision, and see negative one as a negative one, the sigma plus and sigma minus are the two different particles. Same can be to the lambda C decaymetry, and also whether it's symmetry. It's a polarization effect. Okay, I guess I almost done, and with the BESIII selected out. And for the future, we actually published the paper of BESIII in last year. It's gonna summarize the future plan, what it's gonna do. So the target is that we take. So we're gonna we collect 3 billion site twice. After we finish, we already have the 10 billion, and also the future will run energy up to 4.9 G and take data. So it's gonna like, run this machine until another at least 5 years roughly. And also for this 10 billion GSI, you know that we have not really published any results based on this 10 billion GSI. But if you look on the history that with more and more GSI events, we find many new features in Hadron spectroscopy. For example, the XPV bar in the last century, we see a little bit of hint here with roughly 10 times. We see very clear enhancement. And also we see the X1835, and at BESIII we see very clean 1835, but also another new peaks. And with 1.3, we see the distorted line shape around this X1835. So you see that for the 10 billion GSI, you will see that we could see more feature and more interesting things. So we're gonna really make much more efforts to analyze them. And we also have a new plan for the upgrade the BPC2, so-called BESIII. So it's gonna increase this luminosity by 3 times than the BPC2. So with this new upgrade BPC3, we could take data above 3.8 GeV with much higher data taking efficiency, 3 times more, and then we will accumulate more data for the XYZ study and also for the charm biome study. Also, we are now planning the so-called super tau charm factory, which is gonna have roughly 100 times more luminosity and cover a larger energy range from 2 to 7 GeV. And we're gonna realize the beam polarization in order to access some CP variation in tau decay and so on. This is a schematic layout of this collider. This is the storage ring, and this is the collider. This is the collision point and the detector. And it takes 1 immense interval data per year, which is 100 more than the current machine of BPC2. This is the concept design of this detector, which I will not elaborate detail because of the time. At least it will cover all the physics at the BESIII, but also cover them all, especially the CP violation in tau decays, and also rare decay of taus, and so on. So it's going to be still very rich program. If you can see the current BESIII program, you will see much more potential. And this is the planned data set, the expected data set going to taken at the future supercharm. So very promising that we're going to take like 3.4 trillion GeoPsy data. It's going to be like currently we have 10 billion. So it's going to like roughly 300 more GeoPsy data. So it's very ambitious and plan, I think. This is the tentative plan for this supercharm project. We are gonna release a CDR this year, and we already have budget support for the CDR. And now we are going to have the support from the some funding agency for the R&D, and in order to publish the TDR in 3 years. So it's the current plan. It's the construction will start around 2024 and until 2030. So the taking will happen after 2031 and continue 10 years. And then later would be like upgrade of the machine with beam operation with 2 years. So the full data taking year would be like 50 years. This is the international cooperation with this project. So you know that there is also another version of the supercharm tau at Novosibirsk in Russia, and we have already joined efforts on R&D. We have regular meetings, so on. And now we have joined a workshop between China, Russia, and also Europe. So last year we have, due to the pandemic, we have online workshop. So actually we are sincerely welcome the more people to join this effort and to work on this interesting future project. I guess I have taken too much time, so it's come to my summary, and so I will not repeat all this, but one thing that I didn't mention many other interesting results from BESIII because of the really gonna take more time. For example, we published the R value related results and also multi-meson production, which is important input to G-2 calculation, and also fragmentation function and so on. And also there are also many rare decay study and new physics search and so on. So even in the sector I have mentioned, but I still omit many interesting results. For example, the X32 studies and also the global search and so on. So I have to apologize for my ignorance, but I have to say there are many interesting results already published and also gonna be released soon. Yeah. So we hope that we could have more collaboration with Brazil side, and hope to see many friends from the South America to join this Hadron physics campaign. Thank you. That's all.
Thank you, Xiaohui. That is a lot of work going on, indeed. The talk is now open for questions. Are there any questions from the audience? So are there any, if there are no questions from audience, I can ask a few. Let me ask a few questions. Meanwhile, who knows if some people in audience then come up with some questions. So shall we? I had a few. I work more on exotics, so my questions are going to be more on the exotics. I see that you show interesting results on ZC 3900 and 3885. It is still not clear if these two are different or same state.
Yeah, I think there are no conclusion yet. So I'm not sure I can still share my slide, but I did find a button. Yeah, as you see that their mass are close, and there are many theoretical predictions that say that the 3900 is kind of like one model is saying that they could the DDR molecule should have a large decay rate to DD star. So that's why the 3885 is also found in the DD star final state. So they say that they should be belong to one state, which decays to either channel. But we don't know. Actually, this is one model, and the ratio of the decay could be different in different model scenario. The tetraquark compact model or the molecule model. So now they categorize them as one state, but if we for strict speaking, we cannot really take it as granted. Yeah.
I see.
Hi, Kanchan. Concerning this state, I have not a question but a comment.
Yes, please.
This ZCS state, I think we were very happy when you have observed this state, because almost 10 years ago we made a prediction for this state, and the mass and the width, it is very compatible, the observation one with our prediction. So it's just to comment that. And in our work we made predictions for 4 different decay models for this state. So maybe the 2 states are really only one. It's just a comment.
Okay, thank you.
So it seems the same picture is, same confusion seems to be in the case of also 4020 and 4025. In case of still ZC 3900, I remember seeing some papers from the lattice calculations which set some doubt. Like I think if at least in the lattice calculations in molecular model or using a molecular current, if I remember, they did not see the ZC 3900, which caused some doubt. But definitely from the results you show, I think there is no doubt. One might have to just worry is like what exactly the state is. Apparently there are even 2. So that's interesting. Another question I wanted to ask is that you also talked about the lambda C decays to pi sigma and pi kp and other different final states. I was just wondering, just on the basis of symmetry, like the LHCb finds pentaquark states in the lambda b, if you have reconstructed any of the invariant mass, and one could see some lambda, just a strange lambda, some kind of pentaquark structure. Is there any mass invariant information on the mass invariant spectrum of the final states of the CDK?
Yeah, I think this is an interesting things to explore. But Unfortunately, the kinematic phase space for lambda c, which decays to Hadron, is much constrained compared to lambda b. For example, in order to find the counterpart of the pentaquark from lambda c, which one potential channel is the lambda c goes to BESIII phi and pi. Sorry, it's a phi p phi plus a pion. So actually, for this channel, it's this phi is kind of act as a GSI in the lambda b goes to BESIII proton and kaon. So for the proton, for the lambda c goes to proton phi and pion. So actually, the sum of the mass of the three particles already very close to lambda c. So this decay rate is highly suppressed due to the phase space limitation, and the statics are very low, and the p phi in very mass is not. There is no much space to have broader mass range. So we did research and seems not promising because of the much low branching ratio. However, for lambda b, which goes to BESIII proton plus kaon, it have enough phase space to produce this final state, and they could find some interesting feature of the pentaquark. So yeah, that's the thing. For lambda c goes to Hadron pair. Again, as I explained, it's very with very limited phase space. So
I see.
Yeah.
So there is not really much phase space to see some structure there. Maybe also like of lambda 1405, which is kind of well discussed in community, could be like a pentaquark. Could be
Yeah,
open.
that's sure. That is one thing we could do. For example, the lambda c goes to pk pi.
Yes.
In the pk final state. However, it depends on channel. If for the purely charged final state, the lambda b, the RCB actually can do better, because they have much larger lambda c sample than BESIII.
I see.
Yeah.
I see. And maybe one more thing. I see that you have also talked about this new state, which is the ZC with the strangeness, 4000, quite new. And as you discussed, there is already a lot of discussion on it. I wanted to just bring your attention to we also did some work some time ago, which is on hidden charm, but explicit strangeness. So a K-star meson with a hidden charm. We actually study it, and it's like a molecule of X3872 with kaon, or ZC 3900 with kaon. It's a very attractive interaction, and it produces a resonance or a bound state of kind of X and K, or Z and K, kind of coupled channels. The mass is around 4,300. So I was wondering if you have energy, some kind of mass spectrum of like J psi, K pi, where the mass spectrum is around 4,300. In such a region, you could see such a K star. So I just wanted to ask, do you think you have any mass spectrum, any final state of J psi K pi, where actually, if you look in such final states, such a state could appear, which is like a kaon, a K star with a hidden charm, would be interesting for us.
Yeah. Okay. I think we could check that. Yeah, the problem is the production cross section. That's the uncertainty. We cannot say now. So yeah, I think we need because the production cross-section is always hard to predict. So I guess we can still look on that and yeah, to see whether we could see something. Yeah.
I can probably send you some through email our article. It might be interesting for you. Would be interesting.
Yeah, that's very nice. Thank you.
Thank you. So, do we have any other questions from the audience? So, if not, I'm going to thank very much Xiaohui for his time. It's also late night in China, so I'm also not going to keep you up, and we can probably discuss more by email. It has been a pleasure to discuss with you and to listen to your talk, to the results. It was very kind of you. I thank you very much for this talk, and I thank the audience, everyone in the audience, for their presence, for gathering, and it was very nice. I thank everyone around. Yes, Xiaohui, would you like to say something?
Thank you. It's all my honor. Thank you much, Kanchan.
Thank you.
Thank you all. Yeah.
Kanchan, just to thanks Chao for participating in our seminar. Okay, thank you.
Yes.
All right, thank you, madam. Yeah.
And I think before we all leave, I just want to make a small propaganda. Our next talk will be on radioactive ion beams. Margaret, would you like to tell a little bit, a few words before we all leave?
So just the next 13 is Francois de Oliveira Santos talk about the Ganil accelerator, all in invitation. Okay. Wow.
Thank you. The talk is closed.